Well, hi everyone. My name is Kevin Hannon, and I'm going to talk to you about Armada. And I was glad to be invited to give this talk. It's been actually a long way in the making. I met someone at KubeCon Detroit who suggested I give this tech talk back in November, and scheduling overlaps have been tricky, but finally I'm able to do it. So today I'm going to talk to you about Armada, which is a multi-cluster batch scheduler for Kubernetes. So to give you a bit of background into me and introduce myself, again, my name is Kevin Hannon. I actually started my career in chemistry and applied math, and I've mostly focused on utilizing high performance computing, parallel computing workloads to try and simulate chemistry. And I really fell in love with that kind of area of science, and the intersection between science and computer science I thought was super interesting. I decided to actually go more into the software engineering route. So I've been working at a couple different companies. But in the last couple of years, I've started working more on containers and Kubernetes, as probably most people have started using it now. G Research is a fintech company that's based out of London. They just opened their first US location in 2022 in Dallas. But for the purpose of the people in this room, really it's all that what you need to know is they operate a very large research cluster for their quantitative analysts to try and predict how the stock market is going to behave and then trade on that. So really, we are providing a huge platform for our users to run data engineering all the way to machine learning, and trying to provide them the tools to do open source type of workloads. Because in most cases in machine learning, they're using open source tooling and using standard stuff like that. So we want to provide a research cluster for them. Yeah, so generally a batch job it's a huge field. I want to just define it as a finite lifetime job. So that means typically on the order can be really minutes to weeks. As a grad student, I've run jobs that have spent months, and trust me, that was not fun, because you would see constantly your jobs would fail and you have to restart them. And when you start running calculations that long, things like checkpointing are super important, because you probably will have computers fail while you are running these jobs. So generally, so finite lifetime jobs, computational science, machine learning, data engineering, and then genomics. I put genomics because I actually think it's a really interesting use case where the community has really scientific computing is a little bit further behind in containers and Kubernetes than most of the traditional enterprise tech world. But genomics has really propelled this idea of all those solutions for gene sequencing should be containerized and public, so users can bring those down. And I always thought that was pretty neat that and then they have a lot of workflow engines that focus on integrating with different things like Kubernetes or Docker or whatever. And I thought it was pretty neat, so that's why I put that one there. So generally, I think to understand where Armada or why we created Armada, I think it's a good idea to give a context into what G Research was 3 or 4 years ago. So generally, G Research was actually a Windows shop. Primarily, .NET was our primary language of choice. And in the last couple of years, Linux and Kubernetes has really blown up, and they wanted to start migrating off. And also with Microsoft releasing .NET Core, it actually allows you to run .NET on Linux. So there's been an interest to try and migrate our farm from Windows to Linux. And then we also wanted to start adopting containers everywhere. So we are using Kubernetes, as most people use now. But generally, some problems we ran into are and our platform is all on-prem. We don't use any cloud services, so we manage all our Kubernetes instances ourselves. But generally, since we have a fixed cluster size, we need some kind of fair sharing scheduler that really allows our quants to not take over the entire cluster. What we don't want is one developer or one researcher to use the entire farm for weeks and then cause other people to not be able to do their work. So ideally, you want some kind of queuing logic that will allow people to share their resources fairly. And since we provide a research platform that spans the range of use cases, we do provide ways for people to run distributed ML, also data engineering and other types of approaches. So we have to support workloads from single core to multi-node. And generally, I like to think of Armada as a serverless platform for our users. We are providing them an API that you say, give me a container and I'm going to run this job somewhere. I don't care where it is. I don't need to know what hardware it is. I just want to know if I want a GPU, how can I get that scheduled? And that's kind of what we provide. So, but when you provide a serverless platform, you also do need to, there is cases like logs and really the users have to know what happened. Like why is my job stuck? Why did it fail? What are my resources? And so we provide a UI for our users also to understand what's going on without having to know everything about Kubernetes. So generally, parallel compute can be kind of separated into two different approaches. I just want to level set here. Kubernetes has done a really good job of specifying constructs for this concept called embarrassingly parallel. This is where you can imagine splitting your task into individual components that don't require any communication and then process them, and then you can gather them. This is kind of a common pattern for MapReduce or any kind of data workload that you can split up. So this is pretty well represented by most parallel compute frameworks. It's one of the first things they support. You might see things like Monte Carlo. The Kubernetes job tutorial talks about using Monte Carlo to predict pi. That's an embarrassingly parallel job. Also, you can imagine a CI where you want to specify a bunch of tasks to run in parallel. And then once they all finish, you can go to the next one. You can run a lot of tasks in parallel that way. So it's a common case. The other harder one is when you actually want communication between different processes or different nodes. So if you're doing distributed ML, say you want to have 16 GPUs dedicated to training a large language model, which is what all the craze is now with ChatGPT. But generally, you can imagine you need some kind of communication between these processes, and you can't assume you have a single process holding all this compute. So you need a way to communicate between these processes, and this is a lot harder in Kubernetes because the Kubernetes scheduler does not support out of the box gang scheduling or all or nothing scheduling. It will schedule individual pods at a time, and you want to actually make sure you can communicate with those once they're all up. That's tricky to do. So generally, there are two schools of thought and providing a research platform. The traditional way is a high performance computing cluster. And this is actually what the top 500 supercomputers are based off of, or really more of them. If anyone is familiar or has ever worked in a research space, this is the common use case where a user has access to a cluster, they SSH onto a head node or a login node, and then they interface with a scheduler that lives in the cluster, and basically you provide a script that says what kind of resources you want, what executable you're going to run, load that executable into your path, and then run it on the compute nodes. And this is a pretty common pattern. It's really difficult to work with in the cloud space because most users just want a simple API. But instead, with this, you have to SSH onto a node and then actually run a calculation with a scheduler. And then, but generally, like most clusters, like you have compute, storage, and networking. You need all three really to build a high performant cluster. Networking is mostly related to if you're going to be doing communication between your nodes, what kind of bandwidth do you want? And typically you might hear words like InfiniBand or Slingshot as common ways to do more high performant networking. And then storage is actually one of the most important ones. It's really hard to get storage right. In Armada, we have probably one of our biggest problems is our storage. And that can become actually a quick bottleneck because if you can imagine in data or in financial technology, we have a lot of data. We need to read that quickly. And so we need some kind of higher storage throughput. So generally, I wanted to talk a little bit about the SLURM and HTCondor, which are the traditional batch schedulers that live usually on a daemon somewhere on the head node. you can see basically you specify a series of constructs in a bash script, then you tell what executables you want to run, and then you run them, and then they are actually run on the node once the job scheduler requests those. And then HTCondor is the one we actually base this off of. It's one of the only schedulers that's based off Windows, and their focus was more on high throughput computing. But yeah, these are both very common ones that are used still today. And then Kubernetes completely shifts this. If you're a user of Kubernetes, you probably know all you kind of need to have access to a Kubernetes cluster is you need a kube config, and you need to specify. And if you set up your kube config, you can now submit any kind of Kubernetes workload to a cluster. You don't really know where it's running. You can dig into that, but generally you interface with an API, and then that submits to the kube scheduler and then kubelet, and then bam, you have objects running. And it's a much nicer pattern once you know a little bit about Kubernetes. It is a pretty easy way to test ideas. I will give a quick little demo of how you could build a multi-cluster, how you can build a dummy multi-cluster with kind, just in the next slide or two. But it's pretty nice. So generally, Kubernetes does provide a batch job construct. It's called the job API. This was traditionally designed more for embarrassingly parallel workloads, and there's a lot of active areas to try and make this better for HPC/ML workloads. There's a working group in the Kubernetes community actually focused on improving this. I myself have sort of dabbled a bit in helping them. I have a couple Kubernetes enhancement proposals to the job API that I have one that I'm working on right now to try and improve this for the Kubernetes community. So generally, I like to use Kubernetes and Docker or Kind. I just find it's pretty lightweight, and it has worked mostly for my purposes. So generally, I won't give a demo of the job controller, but I can kind of show, you can imagine if you're building a multi-cluster, you have multiple Kubernetes clusters. Well, how can you interface with them? Well, kubecontrol has this idea of a context where you can switch your cluster. And so you can see here, I specify kind demo A, kind adds prepends kind to all these lists. But generally, this is the demo A, and I have a job that I submitted today, and I can look at the pods and get information about that. And same thing for if I want to switch my cluster, I can now switch the context, and now I have a different job with the different pods. And this is pretty nice. If you know the cluster name, you assume they don't change. You always have that right. But what if you're a user and you don't really want to interact with kubecontrol, and you just want to be able to submit a pod or submit a deployment and just have it run somewhere, or really pods in our case. If you submit a pod and you just want to interact with the server and then kind of redirect it to all these different clusters, that's why we ended up building Armada this way. And I will talk more about that now. But so generally, at a low scale, at a normal scale, Kubernetes works really well for the purpose. Like if you don't have too many pods or jobs being scheduled, a single cluster Kubernetes is the way to go. But once you start trying to have more jobs and you have nodes, it becomes really challenging. Like if you imagine if you schedule 1 million pods to a single Kubernetes cluster, there's a finite amount of pods where those nodes can bind to, and then you're going to have a bunch of pods just waiting and pending or waiting to be scheduled. And also, scheduling too many pods can actually overload the internal data server that Kubernetes relies on. We have found cases where we actually can lock up our cluster, and we have to tear everything down and restart it because if we overload etcd. So this is the problem. And there are kind of two ways to do it. One, you can always vertically scale your Kubernetes cluster. OpenAI takes this approach where they have some really interesting blog posts. The Kubernetes documentation also talks a lot about what it takes to actually run large scale Kubernetes clusters. I think GKE, last I heard, they support up to 15,000 nodes. But generally, it's a lot of engineering effort to get that working. And if you're like at G Research, we operate everything on-prem, and we We also don't want to have to do all this engineering effort to scale our nodes and then have them go down. And then, we want to be able to treat Kubernetes like code and roll things out in stages, test out new updates, be able to add clusters when we want, or be able to maybe explore a cloud vendor as Kubernetes with our existing system. So this is kind of why we ended up going multi-cluster. Like for one, we want to be able to limit the amount of blast radius from our cluster. More nodes you add, you deal with more failures, and that is kind of tricky. So we wanted to avoid that. And then, queuing support when you're on-prem is super important because you can't really just burst into the cloud and then just have auto scaling or anything like that. You have to work with what you got. And so a lot of times we want to be able to hold these pods from executing until there's capacity available, because users don't want to wait for days for their pod to be picked up. Or, they would probably wait in a queuing system, but at least you have more control over that. You can penalize people that are submitting too many jobs. And that's kind of the point of a queuing system. I am not saying I'm the only, Armada is the only project. I wanted to talk about another project in the Cloud Native Computing Foundation, which is called Volcano. This takes a different approach where they want to extend Kubernetes via CRDs. They are mostly focused on single cluster, and they actually have their own scheduler dedicated for running batch jobs. And they also have their own queuing logic also. Armada, we took the approach of multiple Kubernetes clusters. We use our own scheduler. We use the kube scheduler from Kubernetes rather than our own written one. And then we also have our own queuing logic. Fundamentally, Armada, you can imagine it at a high level. We have some kind of API that redirects our pods and other resources to Kubernetes worker clusters to actually run the Kubernetes pods. What's interesting about Armada is our users like to use Armada with workflow engines, and generally they actually want an event-driven API rather than a polling one. So we actually provide a way to subscribe to the events of a given workflow, of a given grouping of pods, and then be notified when individual pods are complete. A lot of this is I'm just summarizing a lot of our user guides. If you have more details, you can go on the user guide on our website. But generally, we call a job to mean a collection of Kubernetes resources, and that includes a pod spec, a service, and an ingress, plus metadata related to queuing and job set. Why we actually include a service and ingress is an interesting question. I think a lot of people, when you think of a batch job, you think of just running an executable and then it will just complete. But data scientists want to use things like Jupyter notebooks. You want to have an interactive environment for debugging. You want to be able to, sometimes in the Kubernetes land, you can actually schedule services in a batch job kind of a way. So you can imagine having some kind of microservice you start for a couple hours, and then you can interface with it via a service or an ingress if you have a UI. And so this is actually a common case we have provided. And so that's why in our job, we actually have in the lifecycle of a job, a pod spec, a service, and an ingress. And service and ingress are optional, but pod spec is the one thing we need because we want to be able to use the Kubernetes constructs. Job set is just our concept of a logical grouping of jobs. And then queue is how we do a fair share and also role-based access control for what API verbs are allowed in the Armada API. At a high level, Armada's architecture is users interface with a core server called the Armada server. And this is where users interact with. This is actually where we have a managed Postgres, or we have a Postgres database that allows the users to query what's going on. Also, we provide a UI on top of that, so the users can actually see what their jobs are doing. So once a user submits a pod to Armada server, it is actually leased to an executor, where the executor, which is what we call a Kubernetes worker cluster, actually interfaces with the Kubernetes API to submit pods, services, ingresses, and it cleans those up once the pod is complete. This is also how we get logs from our pods. And so generally, this is a pretty this is a kind of a familiar pattern. If you have ever interacted with the Kubernetes cluster, you're going to create a pod spec, you're going to create a deployment, you're going to create all these, and you interface with an API. And this is kind of where the executor is programmatically doing that, and then reporting back the information that the server needs for our users. Why? And one other powerful thing of multi-cluster is we want to be able to add new Kubernetes clusters whenever we have more machines, and we don't want to have to take down the entire farm in order to do that. So we can actually add and remove clusters without taking down our entire environment, and that has been actually very helpful for rolling out new ideas and also doing rolling rebuilds of our nodes. So you can imagine with Q, I talked a lot about fair sharing. Another area also, if you have a batch job scheduler, you can imagine you might have users that want to, like, our quants are very hyper competitive with one another, and they're trying to have the best prediction for the stock market, and that's how they make their money. And they generally we have to provide cases where user A is not going to cancel user B's jobs and vice versa. And so we want to provide like role-based access control and some of the Armada API limitations, like which users are able to submit jobs, which users are able to look at the logs of other people's jobs. So this is actually pretty important. This is how we tie our user information into our authentication layer. And generally, some cases we have quants that go on paternity leave. They have kids, and then they don't want to think about their jobs, but then their jobs are still running, and then they're causing a problem. So we have some cases where admins are allowed to cancel those jobs if they are on leave for the next couple months. And so this provides, you can imagine, like a hierarchical way of providing some information for this from an admin perspective. As I mentioned, pod specs are Kubernetes constructs. So this is how we allow our users to mount volumes, taints, tolerations if they want to try and request a GPU or other kind of resource or specify a particular node. We also make heavy use of labels and annotations. Our UI is open-ended and will display labels and annotations in a pod spec because we found that users want more information about what the job looks like. And then also, again, we allow stuff like ingress, namespace, and all that. So one thing that, as I mentioned with GR, we were primarily a .NET company, so we had to provide out of the box a .NET client for interfacing with Armada. And we also provide a Go client and an Armada control CLI. I'm happy to say that as part of the Cloud Native Computing Foundation, we actually were able to join the Google Summer of Code initiative, and we have a couple proposals going on to make Armada part of Kube Control via Crew plugin, and we're excited to have some new developers take that work on. I've been leading the initiative for getting that, and I think it's pretty exciting to see hungry new developers working to try and implement features in the open source way, and I've been happy to read some of those proposals. But anyway, one of the reasons why we actually created the Python client is because we do a lot of workflow scheduling in-house, and it is kind of a burden. As some of you know, there are hundreds of workflow engines out there, and I'm sure G Research probably has at least 20 or 30 that they wrote in-house for themselves. And it is unbelievably complicated, and trying to get all these different schedulers to work together is challenging. And then some are hyper specialized for one case, you understand. So we built the Python client in order to interface with Apache Airflow, because we actually at G Research really like the idea of workflows as code and really anything as code. And Airflow provides a nice way where you define a Python DAG, and then you upload it to a GitHub repo, and then Airflow will actually monitor that DAG and then execute it at the scheduled time that you want it to run. And then it also provides a nice UI for people to understand what's the overall view of all their tasks. And but generally, the way Airflow provides, if you're building an open source project, you always want to think about how other people can extend it for their purposes. And Airflow really did a great job providing a nice, clean API for integration. It took only a couple hours to create, or maybe not even that, to create an operator in Airflow because they provide a base class that you can inherit from, and then you just implement one function called execute. And then the hard part for us was Airflow requires waiting for individual tasks to complete before going to the next one, which is a little challenging to do in an event-driven architecture. So we had to do a lot more work on our end to interface with Airflow, but the API for Airflow is actually really simple. I will give a demo of the Airflow integration at the end of this talk. But yeah, so this is a simple DAG where I'm just running a hello world and then followed by Armada, which is another hello world. And these are just sequential tasks. Jupyter, I mentioned, is another use case where users actually they can submit via the Armada API, a pod, an ingress, and a service. It goes to the Armada server. Then it goes to a Kubernetes worker cluster. Then the user is actually able to use the URL that the ingress and service provides, and then they can now interact with their Jupyter notebook on a Kubernetes cluster. And then once the job is complete, it's all cleaned up for them. And so this is actually a pretty common use case in data science and machine learning. It's one of the first entry points for people doing exploration. Yeah, I won't be able to give a demo of Jupyter, but if you have any questions, feel free to Slack me or ask on our Armada Slack channel. So I want to talk a little bit about some different, I already mentioned the Kubernetes working group that's focused on adding batch capabilities in Armada and Kubernetes. I myself take some part in that. I help, I work a little bit on some of these feature ideas, not as much. This is actually led by the Kubernetes community. In particular, SIG scheduling has created a new, it's a joint effort among many different Kubernetes communities, including SIGApps, SIGNode, and SIG scheduling, and it's a very interdisciplinary working group. So queuing is the first thing they added, which is called Q. They had a project called Q with a K, Q with a K. And this is where they're adding queuing capabilities into Kubernetes in a native way. They're also taking feature requests and trying to improve the job API for all the different use cases because they really want to they want to discourage people from scheduling raw pods, and they want to use some kind of higher level controller that will provide the constructs for a batch, for business rules for batch jobs. And then the research user group is a common place for researchers to share ideas around running research workloads on CNCF architecture, on CNCF tools. It's a fun little group to hear about where groups like CERN, how they're running their workloads, and other different research groups. And then I'm taking part in a batch working group where we're trying to provide a white paper for best practices around batch and Kubernetes. Also making sense of all the other different batch schedulers out there. Like SLURM, I mentioned, I didn't really talk much about SLURM other than here's the API, but they are also actively working on understanding how SLURM could take a Kubernetes job or Kubernetes pod and run that on their scheduler. And so we're trying to have a little survey of where people are, what options there are, how we can better share ideas among the different scheduling working groups, among the different scheduling groups. And then we have Armada, our project, Armada project / Armadas or GitHub. And then we have we have a Slack under the CNCF workspace, the Cloud Native Computing Foundation workspace. We have a channel called Armada. That's where we hope to have questions asked about Armada. And I'll give a quick little demo. This is the demo I'm running. Again, we are a gRPC API. So this is kind of how you inject auth layer into, authentication and SSL into gRPC. But then once you run this is our API where we're submitting 100 jobs to the Mirantis queue, and then they're running. So generally, we have a website called Armada Project, and then we have a demo that is running on EKS for the purpose of people exploring how this looks. I mentioned we have an API we have a UI called Lookout, and this is kind of where users can interface with this. And then this is my queue. And so now you can see I have one pending job, and then 99 jobs have already succeeded. And this is our logical grouping of jobs. And then I can go to the jobs queue, and now you can see a list of all the jobs that have run. And then if I click on these, it hyperlinks to some information around the pod spec and what these jobs actually look like. You can see here what kind of cluster it ran on, what's the state, and then what is the actual job that you submitted. You can see it's a pretty simple one, nothing too complicated. And then you can see now the jobs have all complete. And now what does it look like for, and I mentioned Airflow is another case where we, Airflow is again a DAG you have workflows as DAGs, workflows as code. And then now I can click on an individual Airflow DAG, and then I can run it. I click on this plus. Looking at this code, you can see this is very similar to what I submitted. I specify an Airflow DAG, and then I specify my gRPC client. And then I specify two task in Airflow, and then create a DAG. And then I can use Airflow's UI to actually view the status of these jobs, and then go to logs, and you can see this. Did not quite get that one working, but I can go to Lookout also, and sorry, I'm trying to remember what it was called. Yeah, you can see here is the queue. The Airflow one I can tell is because Airflow titles their job sets as manual. And then you can see here, it actually tells me what Airflow DAG it was. And I added some annotations to allow more flexibility for users to add their own user annotations. And that is my talk. If anyone has any other questions or is interested in checking this out, I recommend you can go to the Cloud Native Computing Foundation. You can go to the Armada channel. This is where we hang out. And then our website, armadaproject.io, gives you some information around Armada. And then our repo is on GitHub. So if you have any questions, please feel free to check it out. And I thank you all for your time. I will give you back some time.